Section 13.5 Changing Equilibrium Conditions, Le Chatelier's Principle. We have seen that when a reaction reaches equilibrium, the rates of the forward and reverse reactions are equal and the concentrations remain constant. Now we'll look at what happens to a system at equilibrium when changes occur in reaction conditions, such as changes in concentration, volume, and temperature. Le Chatelier's Principle. When we alter any of the conditions of a system at equilibrium, the rates of the forward and reverse reactions will no longer be equal. We say that a stress is placed on the equilibrium. When the equilibrium responds by changing the rate of the forward or reverse reaction in the direction that relieves the stress to reestablish equilibrium. I'm going to read that again. We say that a stress is placed on the equilibrium. Then the system responds by changing the rate of the forward or reverse reaction in the direction that relieves the stress to reestablish equilibrium. We can use Le Chatelier's principle, which states that when a system at equilibrium is disturbed, the system will shift in the direction that will reduce the stress. Le Chatelier's principle. When a stress, a change in conditions, is placed on a reaction at equilibrium, the equilibrium will shift in the direction that relieves the stress. Suppose that we have two water tanks connected by a pipe. When the water level in the tanks are equal, water flow in the forward direction from tank A to tank B is at the same rate as it flows in the reverse direction from tank B to tank A. Suppose we add more water to tank A. With the higher level of water in tank A, more water flows in the forward direction from tank A to tank B than in the reverse direction from tank B to tank A, which is shown in the longer arrow. Eventually, equilibrium is reached as the levels in both tanks become equal, but higher than before. Then the rate of water flows equally between tank A and tank B. Water at equilibrium. Stress at water is added to the first tank, increasing the rate of forward direction. New equilibrium established. When the water is added to one tank, the levers readjust to equalize. Effect of concentration changes on equilibrium. We will now use the reaction of hydrogen and iodine to illustrate how a change in the concentration disturbs the equilibrium and how the system responds to the stress. In the reaction, hydrogen plus iodide yields 2HI. Suppose that more of the reactant hydrogen is added to the equilibrium mixture, which increases the concentration of hydrogen. Because the Kc cannot change for a reaction at a given temperature, adding more hydrogen places a stress on the system. Then the system relieves the stress by increasing the rate of the forward reaction. Thus, more products are formed until the system is again at equilibrium. According to Le Chatelier's principle, adding more reactant causes the system to shift in the direction of the products until equilibrium is reestablished. So adding hydrogen will gain more product, and it shifts to the right. Suppose that some of the hydrogen is removed from the reaction mixture at equilibrium, which lowers the concentration of hydrogen and slows the rate of forward reaction. From using Le Chatelier's principle, we know that when some of the reactants are removed, the system will shift in the direction of the reactants until equilibrium is reestablished. If you remove some of the reactant, the equilibrium shifts to the left. The concentration of the products of an equilibrium mixture can also increase and decrease. For example, if more hydrogen iodide is added, there's an increase in the rate of the reaction in the reverse direction, which converts some of the products to reactants. The concentration of the products decreases and the concentration of the reactants increases until equilibrium is reestablished. Using Le Chatelier's principle, we see that the addition of a product causes the system to shift in the direction of the reactants. So adding product shifts to the left. In another example, some HI is removed from the equilibrium mixture, which decreases the concentration of the products. Then there is a shift in the direction of the products to reestablish equilibrium. Removing product will shift in the direction of the right. Figure 1311. The addition of hydrogen places stress on the equilibrium system of hydrogen plus iodide yields 2HI. To relieve the stress, the forward reaction converts some of the reactants of hydrogen and iodide to product HI. A new equilibrium is established when the rates of the forward reaction and the reverse reaction become equal. In summary, Le Chatelier's principle indicates that a stress caused by adding a substance at equilibrium is relieved when the equilibrium system shifts in the reaction away from that substance. Adding more reactant causes an increase in the forward reaction of products. Adding more product causes an increase in the reverse reaction to reactants. When some of the substance is removed, the equilibrium system shifts in the direction of that substance. These features of Le Chatelier's principle are summarized in Table 13.4. An increase in reactants causes a shift in the direction of the products. A decrease in reactants causes a shift in the direction of the reactants. An increase in products gives a shift in the direction of the reactants, and a decrease in products gives a shift in the direction of the products. Effects of a catalyst on equilibrium. Sometimes a catalyst is added to a reaction to speed up a reaction by lowering the activation energy. As a result, the rates of both the forward and reverse reactions increase. The time required to reach equilibrium is shorter, but the same ratios of products and reactants are attained. Therefore, a catalyst speeds up the forward and reverse reactions, but has no effect on the equilibrium mixture. Effect of volume change on equilibrium. If there's a change in the volume of a gas mixture at equilibrium, there will also be a change in the concentration of those gases. Decreasing the volume will increase the concentration of gases, whereas increasing the volume will decrease their concentration. Then the system responds to reestablish equilibrium. Let's look at the effect of decreasing the volume of the equilibrium mixture of the following reaction. 2 carbon monoxide plus oxygen yields 2 carbon dioxide. If we decrease the volume, all the concentrations increase. According to Le Chatelier's principle, the increase in concentration is relieved when the system shifts in the direction of the smaller number of moles. So the reactants have 2 moles of carbon monoxide and 1 mole of oxygen, which is 3 moles of gas. The products, there are 2 moles of carbon dioxide. So if you increase the concentration, it will shift away towards the lower number of moles. On the other hand, when the volume of an equilibrium of gas mixture increases, the concentration of all the gases decrease. Then the system shifts in the direction of the greater number of moles to reestablish equilibrium. So increasing the concentration will shift, or increasing the volume, which is increasing the volume, which is decreasing the concentration, shifts back towards the higher number of moles, which is towards the reactants. Blah, blah, blah. When a reaction has the same number of moles of reactants as products, the volume's change does not affect the equilibrium mixture because the concentration of reactants and products change in the same way. The effect of change in temperature on equilibrium. We can think of heat as a reactant or a product in a reaction. For example, in the equation for an endothermic reaction, heat is written on the reactant side. When the temperature of an endothermic reaction increases, the system responds by shifting in the direction of the products to remove heat. So heat is used just like a reactant. So increasing reactants shifts away from reactants. Increasing heat, if it's endothermic, shifts away from that, and so it will shift towards products. If the temperature is lowered for an endothermic reaction, there is a decrease in heat. Then the system shifts in the directions of the reactants to add heat. In the equation of an exothermic reaction, heat is written on the product side. When the temperature of an exothermic reaction increases, the system responds by shifting in the direction of the reactants to remove heat. If the temperature is lowered for an exothermic reaction, there is a decrease in heat. Then the system shifts in the direction of the products to add heat. Table 13.5 summarizes the stresses that you can use Le Chatelier's principle to determine the shift in equilibrium that relieves the stress caused by the changing condition. When a reactant is added, it shifts towards the product. When a reactant is removed, it shifts towards the reactants. If a product is added, it shifts towards the reactants. If a product is removed, it shifts towards the products. If the volume decreases and the concentration increases, it shifts towards the fewer moles of gas. If the volume increases, which decreases the concentration, it shifts towards the more moles of gas. If the temperature of an endothermic reaction raises, it shifts towards the products. If the temperature of an endothermic reaction lowers, it shifts towards the reactants. If the temperature of an exothermic reaction raises, it shifts towards the reactants, and if the temperature of an exothermic reaction lowers, it shifts towards the products. The addition of a catalyst increases only the rates, but it has no effect on the stress in either direction because the rates are going to be coming up equally.